1990 number 2 is a great question that reviews some of first year physics and also gets us into some of the second year physics that we've been doing. So, part A should be a little bit more straightforward. We have a block at the bottom of an inclined plane, and we want to know the maximum height to which it will rise in terms of the given quantities and appropriate constants. In this case, we can simply say 1/2 mv0 squared equals mgh. We're just conserving energy. And so we're just going to get that v0 squared over 2g is the height. That is fairly straightforward. Things get a little bit more interesting in part B, where there's a number of ways we can do this, but I'm going to actually use conservation of energy and talk about some of the dissipated energy done by friction. And to calculate exactly what that is, we'll just note that the E dissipated by friction is going to be the work done by friction. And since this is an inclined plane, I'm hoping that we're at a stage here where we feel comfortable saying that mu times the normal force is the force of friction. So we can say the force of friction is going to be mu mg cosine of theta. For those of us who are still a little rusty on that, remember this is Fn, this is Fg. We have the friction force going this way, and we can split Fg into two components, mg cos theta, mg sine theta. And so we can actually say that the force of friction is mu times the normal force. And so that's going to be mu mg cosine of theta. Now, the distance up the inclined plane that this thing goes. So the distance up the inclined plane, because that's times, so the work done by friction is going to be force times that distance up the inclined plane. And that's going to be mu mg cosine theta times the letter d. And I'm going to write that in a little bit of a different color, because what I'm going to do is I'm going to go over here and we're going to figure out what that actually is. So let's go from, this is h, and we start here. So this distance is what we'll call d, and h is the height to which the object rises. D is the distance over which friction does work. So this is the distance of work done by friction. And let's use SOHCAHTOA. So we know h over d equals the sine of theta. So the distance in question is going to be h over the sine of theta. And I'm actually going to use that right here. So the work done by friction that we will use is, and that's the E dissipated, is going to be work equals mu mg cosine theta times h over sine of theta. And so keeping all of this in mind, the work done by friction is going to be mu mg h times the cotangent of theta. We haven't even done part A yet. I've just got the work done by friction because that's going to be, in part B, that's just the work done by friction. So let's go ahead now. We're going to basically say that E kinetic gets turned into E gravitational plus E dissipated. And so that means 1/2 mv squared is going to get turned into the mgh work done by gravity, and this is v0 squared, plus the mu mgh cotangent of theta work done by friction. So we see that m's cancel. We're trying to isolate h. So we're getting v naught squared over 2 equals g, parentheses, actually, sorry, 1/2 v naught squared equals, I'm going to factor out h here, and this is going to be g plus mu g cotangent of theta. So overall, let's go ahead and now we'll isolate h up here. When we solve, all of this, what we'll see is h equals v naught squared over 2 g plus mu g cotangent of theta. And that is our answer to part B. All right. Now, if the incline is rough, one thing we should say, I should give you the moment of inertia for a hoop. And for a hoop, the moment of inertia is plain old mr squared. So for part C, what we're going to say is, as we roll up the hoop, we're going to have it rolling while it slides, rolling without slipping. So it's going to have E kinetic translational, which is the 1/2 mv squared, plus E kinetic rotational, and it's simply going to end up with the height mgh. Let's go ahead and plug all that in. So we're going to have 1/2 mv naught squared plus 1/2 I for a hoop times omega squared is mgh. Now we've got a couple simplifications to make. We're going to take 1/2 mv naught squared. That's going to stay the same. But then here, for I, we're going to put mr squared for the hoop. And for omega squared, that's v naught over the radius of the hoop squared equals mgh. If we simplify this further, we're going to get 1/2 mv naught squared plus 1/2 mv naught squared equals mgh. And so we're going to get a height of v naught squared over g is the height. One thing I want to note is, if you notice, compared to part A, it actually goes higher up. And that's because to have a speed v naught while you're spinning means you actually have more kinetic energy total that can get transformed into gravitational energy. So it ends up going twice the height. Now for part D, this is a trick question. No friction means no spinning. You actually need friction for spinning to happen. And the reason we know that is friction applies the torque to make things spin. So it turns out in this case, v squared over 2g is going to be the height that we have. So that's part B, and we'll take a look at part E in the next video.